we started with the pyranometer, which measures the global radiation, which is sum of the uh, beam radiation and diffuse radiation. Then, in case one is interested to measure diffuse radiation, the combination of the pyranometer and shading ring can be used. And if beam radiation is to be measured directly, then a pyrheliometer should be used. So what are the components of that? The construction details and the principle of measurement, etc. were discussed. Then it was told that the value that is available from these measuring instruments can be taken as the instantaneous value, but generally the instantaneous value does not have much importance unless you are carrying out a limited period experiment with readings at different readings at certain interval and the sky is clear. But the data for the cumulative values of the solar energy available may be of more importance, because it gives you the potential of putting up a solar collector. The output potential can be estimated with the help of that kind of data. So that thing can be presented with the help of a graph shown here. So you can see how the irradiance, if you don't have, if you don't have too much of disturbance in terms of the clouds in the sky, this is the pattern, solar irradiance pattern that you might expect on a particular day, and the cumulative value is shown with the help of this blue curve. So the instantaneous value, the irradiance, is measured in, or can be measured in watt per meter square. So as you can see, what could be the range in which it is available, and the cumulative value is the energy value, right? So what is joule per second, and when you measure it over an hour, so it, like, you can multiply, like if you are taking reading at each second, then the average of that whole hour may be multiplied with 3600 second, then you will get it in joule per meter square, and then you may convert it into kilojoule per meter square or megajoule per meter square, and again, like, you are going on adding it for multiple hours, and finally one might be interested in the total energy that was available per meter square area in the whole day. So that may be expressed as megajoule per meter square. That is one of the units which might be used, and or a kilowatt hour also may be used, right? So if 1 kilowatt energy is available for 1 hour, then the 1 kilowatt power is available for 1 hour, then the energy that you get is 1 kilowatt hour. So the other unit which might be used is kilowatt hour per meter square. So with the help of such data, which is measured continuously over the whole year and over multiple years, one is able to produce the tables like this. So you can see a table where the solar global radiant exposure, that is nothing but the global radiation energy available in megajoule per meter square, is given, and for our how many megajoules per meter square are available are tabulated here. Okay. So with the, like, over a day or in a particular period, let's say you are interested from the period 9 a.m. to 5 p.m. or 6 p.m., then you can just add all these values, and that will give you how many megajoule per meter square is available in that span of time. Okay, so this data can give you the potential or the availability of solar energy. Of course, these things are what is available on a horizontal surface. What is available on horizontal surface, because the weather stations most of the times present the data for the horizontal surface. Then that can be used to evaluate or to calculate the value that would be available on an inclined surface. So we will be taking one such example now. Okay, this is for a table for diffuse radiation. So now let us talk about solar radiation on an inclined surface. Now, if you recall, in previous lecture, a diagram was shown where a pyranometer was put on an inclined surface. Now, if you are measuring the radiation, the total radiation on an inclined surface using a pyranometer, then this type of calculation is not necessary. This type of calculation would be necessary if the value of radiation, beam radiation and diffuse radiation, is available for horizontal plane. If it is available for horizontal plane, then and your solar collector is inclined or is tilted at an angle beta, in that case you would need to do this type of calculation. So this should be very clear in your mind. Now, what is the reason why we keep the collector inclined? That was understood with the help of an example, and you could see that the angle theta, that is the incidence angle theta, came out to be smaller than the zenith angle theta z, right? So now you can say that more amount of energy, solar energy or radiation, is available on that collector which was inclined to the horizontal plane. The same thing may be represented like this. If you have the data for the horizontal plane and you want to get the radiation input that in different parts, beam, diffuse and reflected, then how can you calculate the energy available on an inclined plane? There will be three parts of it. 1, beam radiation, 2, diffuse radiation, and 3, because it is inclined, there will be some reflected radiation also available on that plane. So beam radiation value that would be available on horizontal plane need to be modified for the collector which is inclined at some angle to the horizontal plane. So what is that modification? It may be called beam radiation factor. So beam radiation factor is the ratio of cosine of incidence angle to cosine of zenith angle. Okay. So mathematically you write it like this: gamma b, the beam radiation factor, is equal to cos theta upon cos theta z. So from notations now you know that theta is equal to incidence angle and theta z is equal to the zenith angle. Now, what about diffuse radiation? Again, try to recall the diagram that was shown in the previous lecture. An inclined line, and so inclination or tilt is equal to beta. Okay, tilt is equal to beta. Then what do you think? Like, now we are talking about the diffuse radiation factor. Now we are talking about diffuse radiation shape factor. So whether that value would be greater than 1 or less than 1. Let us talk about this value, theta, cos theta upon theta z. Now there are chances that theta sometimes may be less than theta z or otherwise also. So it's possible that your gamma b has some value less than 1, but most of the times you will keep the collector inclined such that your theta comes out to be less than theta z, and in that case your gamma b is more than 1. So the purpose of making the collector inclined is to get beam radiation factor greater than 1, so that for that collector, which is generally a fixed collector, at a given point of time, or when there is a need for energy for that period of time, energy or solar radiation is available higher than what would be available on horizontal plane. Okay, so you can expect that if you are talking about the right time and proper angle, angle beta used, or a proper tilt angle for the given collector, then your gamma b should be greater than 1. Now what about the diffuse radiation shape factor? The value is 1 plus cos beta upon 2. Now, what could be the maximum value of cos beta? Obviously 1. So 1 plus 1, 2 divided by 2. So the maximum value of diffuse radiation shape factor is 1 when beta is equal to 0 degrees. Beta is equal to 0 degrees means the collector is horizontal. The collector is horizontal, right? So a horizontal collector always gets the maximum amount of diffuse radiation. The reason is that the horizontal collector or a horizontal surface is able to view the whole hemisphere 180 degrees of the sky, and assuming isotropic sky, that is equal amount of radiation coming from all directions 180 degrees, you would get all the radiation coming from the sky on a horizontal surface, diffuse radiation. Now when you make the collector inclined, your collector cannot see the sky behind it. Your collector cannot see the sky behind it. So your beta now is not equal to 0. Cos beta value would start decreasing, and your gamma d value will also be less than 1. So when you are making the collector inclined, you are sacrificing some part of diffuse radiation. The other extreme could be that you keep your collector vertical, right? 90 degree could be the maximum tilt. You are not going to make it invert. You are not going to use it inverted, right? So 90 degree would be maximum. Now at that time, your gamma d is equal to 1 half or 0.5, 1 plus 0 divided by 2. So 0.5. It means that a vertical collector cannot see half the sky. The half the sky behind it, the solar or diffuse radiation is not available. Right, so the value of gamma d would be between 0.5 and 1. 1 for the horizontal collector and 1 for the horizontal collector, and the value would be how much? 0.5 for the vertical collector. So that is about the diffuse radiation shape factor. Now there is another factor called reflective radiation shape factor. Reflective radiation shape factor. Now this reflective radiation shape factor is giving you a fraction that would be available because of the reflected radiation shape factor. Yes. So this is reflected radiation shape factor. Now, how much reflected radiation would be available? It would be how much is coming from the ground and being received by the collector. I think I should go to the diagram which I have been mentioning again and again, right? Or I should have put it here. Right. So I'm talking about this diagram. So this dashed line may be assumed to be your solar collector, which is inclined or made or tilted at an angle beta. So when you make it inclined, your IB gets modified and you expect that you will get more radiation, beam radiation on this inclined plane as compared to the horizontal plane, because your incidence angle might be less than. Incidence angle is the angle between the normal to the collector plane and the sun ray. So you expect that that is less than the angle made between the zenith and the collector, right? So that's about the beam radiation shape factor. Now the diffuse radiation shape factor. So as you can see, the sky behind this collector on the right hand side, it cannot see that. So that is expressed as 1 plus cos beta by 2, right? And extreme cases, if you keep it vertical, it cannot see half the sky, right? So it will become 0.5. So that's about the diffuse radiation shape factor. Now, as you can see here, they have shown the reflected radiation. Now, how much is falling on the ground? It is the total radiation, that is sum of beam and diffuse, is falling on the ground. Now, what part of it is reflected? It depends upon the reflectivity of the ground. So that is expressed with the symbol rho. So rho for clay and grass, it is taken as 0.2. So 20% of the total radiation that is falling, that is IB plus IG as measured on the horizontal plane, 20% gets reflected and it can be received by the collector, right? So that is what is available on the on this inclined plane. But then how much would it actually receive? It will again depend upon the angle beta. So it will be 1 minus cos beta by 2. That is what it can receive. So let's go to that formula. So reflected radiation shape factor is rho into 1 minus cos beta upon 2. So this rho is point, generally we'll take, unless given, we'll take it 0.2, 1 minus cos beta upon 2. So if your beta is equal to 0, that is horizontal collector. So cos beta is 1 and your reflected radiation is 0. Right? So horizontal collector cannot see the ground. We are only considering the reflected radiation coming from the ground. We are not talking about like if there are some surrounding tall structures, they may be reflecting and giving the radiation to the collector. We are not discussing that case. It will be a very complicated case. Okay, so if the collector is horizontal, then it will not receive any reflected radiation. Extreme case is 90 degrees. So in this case, it will be 0.5 into rho, right? So 0.5 into, let's say, 0.2, right? So that will be 0.01, right? So that's the maximum value of this gamma R that is possible, right? Now, finally, how much is the total radiation available on an inclined surface? IT is the total radiation available on an inclined surface. So that is equal to IB. Now this is what is measured on horizontal plane. IB measured on horizontal plane multiplied by gamma B, that is the beam radiation shape factor, ID into gamma D plus IG. IG is the total radiation falling on ground, and out of that, how much would be received by the collector? It will be equal to gamma R. So with this formula, you can get the total radiation available on an inclined surface when the radiation is measured on horizontal plane. IB and ID value are given for the horizontal plane, but your collector is inclined. So in that case, you need to use this formula and find out how much is the input to my collector. That's the input energy to your collector. So now let's take this example, which will involve small calculations. Right. So you, I believe you might be ready with your calculator, pen and paper. We have adopted the data from the previous example that was solved. If you recall, a collector at New Delhi and made inclined at an angle, that is tilt angle is equal to the latitude angle of that place. So tilt angle in this case is 28.49 degrees, which is actually the latitude angle of Delhi. And these were the final answers that we got, and it was that the incidence angle was 32.79 degrees and the zenith angle was 44.35 degrees, right? Now let's say the beam radiation and diffuse radiation are measured on horizontal plane. Okay, if beam and diffuse radiation as measured on horizontal plane are 600 and 200 watt per meter square respectively, find total radiation falling on surface of this collector. So now you have the required formula for calculations. This IB is given as 600 and gamma B is to be calculated, right? So let's do it step by step. You won't do all the summation at a time. Calculate gamma B first, and you can post your reply in the chat box. So gamma B for these two angles, you can write down which are the angles that you are talking about. Theta is equal to 32.79 degrees and theta Z is equal to 44.35 degrees. So write down these two angles, theta and theta Z. And how much is gamma B? Gamma B is equal to cos theta upon cos theta Z. So get the value of gamma B and tell me what is the number you are getting. Later on we'll multiply it with IB and get the first term. So cos theta upon cos theta B, how much is the answer or the value?
$1.17.
Okay, so somebody told 1.17. Let's see how much is the value that you get. Yeah, so there is, like, seems that was some rounding of error. As I have written, it is 1.176. So what does it mean? It means that, yes, so somebody has posted 1.175. That seems to be closer to this 1.176. Okay, so you should be close to this. Even if you write 1.17, no harm in that. Right, having the calculation and formula right is more important than the precision or the accuracy of the answer. So 1.176, what does it mean? Your gamma B is 1.176. Now on horizontal plane, how much is beam radiation available? Beam radiation is available 600 watt per meter square. But on your inclined collector, it would get enhanced by 1.176, means around 17.6% extra radiation, beam radiation is available because the collector is inclined at an angle 28.49 degrees rather than keeping it horizontal. So at this point of time, it shows that yes, there is benefit in keeping the collector inclined, at least from point of view of beam radiation. And generally, of course, if you are talking about a flat plate collector, you are taking the diffuse part also as input energy, but there are certain collectors where only the beam radiation is important. It is not able to utilize the diffuse part. So in that case, this term will be even more important. But even for this, the increase. Now this is again higher. Beam radiation normally is higher, right? Unless it is like too dusty or cloudy, a beam radiation component would always be higher, and you are enhancing that higher value. So it's generally important to keep the collector inclined at such an angle so that you get the high or good amount of enhancement of beam radiation. So as you can see, it has been enhanced. Okay, now let's see what is the value of this diffuse radiation shape factor, 1 plus cos beta by 2, right? Your beta is equal to 28.49 degrees. So what do you expect? You expect it to be less than 1 or more than 1? And how much is the value that you get, gamma D? So you can post it in the chat box.
What is the value of beta? 28 point?
Yeah, beta is the tilt angle, 28.49 degrees. Yes, so Ujjwal writes that as 0.939. Okay, 0.939. Yes, I feel that should be correct. Yeah. So here it seems I have done some rounding off. So I've written it as 0.94, right? So 0.939 is very close to that. So must be correct. Okay. Now, so what does it mean? This diffuse radiation, you can see it has not reduced too much. This is not much away from 1. It means that you have sacrificed only 6% of diffuse radiation, right? If it is horizontal, then you get 100%. That is gamma D is equal to 1, but here it is 0.94. So only 6% is sacrificed, and again, diffuse radiation component is lower. It is just 200. So you have sacrificed 6% of that 200. So that's not a big sacrifice, right? So this is the reason why it like if you make it inclined at the proper angle, it would be generally advantageous. And what about the diffuse radiation? How much do you get it? Whether you get a significant amount of reflected radiation or you don't get the significant amount of reflected radiation. So that you can calculate with the help of the formula for this gamma R. So your rho may be taken as 0.2 cos or 1 minus cos beta. So beta again 28.49 degrees, and you can get the value of gamma R, the reflected radiation shape factor. So let's have the value of gamma R, the reflected radiation shape factor. Yes, so Ujjwal says that it is 0.012. Yeah, so seems to be a very small number, just 0.012. Yes, so let's check. I hope that's the correct value. Yes, 0.012. So what does it mean? You might feel that yes, you are getting some reflected radiation, but then it's a very small part, right? It is 0.012. Right? So this gets multiplied with the total radiation, of course, gets multiplied with 600 plus 200, that is 800, but 800 into 0.012, right? So out of the total 800, only 1.2% of that is available on your inclined collector. So this is again a very small contribution, right? So you may now put the values here and get the total value, which should be somewhere close to 903. So as you can see, if your collector is horizontal, how much would you get the total radiation? 600 plus 200, so 800 watt per meter square. When you made the collector inclined at angle beta, you increase the beam radiation availability, you sacrifice little bit of diffuse radiation availability, and you increased a very small negligible amount of reflected radiation, and finally you got 903 watt per meter square on that inclined collector. So in place of 800, now 903 is available. That is obviously you are getting higher radiation, the total radiation on that inclined surface. So that's an increase of around 13%. Okay. So this example demonstrated how you can calculate the amount of total energy incident on an inclined collector when you have the values for beam radiation and diffuse radiation available on horizontal plane. Okay. So let's go to the other part. We are not going into this estimation of solar radiation. So this brings us to the end of the first chapter, which discussed the basics or different like geometrical angles, the sun-earth geometry, as well as solar radiation measurement, okay, and calculations. So this is the basics of solar energy, and now you are equipped to understand the principles and the whys, the construction details, the functioning, etc. of different type of solar collectors. Right. So I would give you some questions as assignment for the previous chapter. So yeah, the syllabus mentions solar energy as a single chapter. I have just divided for convenience into two parts because it's a bit lengthy chapter, and again conceptually also you can divide it into two parts. So I've divided it into two parts. So now you are talking about the utilization of energy, solar energy. Until this point you were talking about availability of solar energy on a particular surface, on the surface of Earth. Okay, now you wish to utilize it. So basically you are going to convert one form of energy, that is the energy available in the form of radiation or electromagnetic waves, into electrical energy or into heat energy. Okay. So energy conversion is taking place. Now when a solar radiation or any radiation for that matter, when it strikes a surface, what happens to it? There are three things which might happen when it strikes a surface. One, a part of it gets absorbed. Second, a part of it gets reflected, and third, a part of it may get transmitted through that surface. Let's say you are talking about some glass material. So in that case, your transmissivity is, let's say, 90%, and 5% absorptivity and 5% reflectivity. It means that out of the total radiation striking that glass surface, it allows 90% of it to pass through it. It absorbs 5% of that, and what it absorbs gets converted into heat, right? And what happens to that heat? Like it is generally lost to the surroundings, and a very small part may enter into the solar collector. Sorry, this is reflected, so it is totally lost, and absorbed, what happens is glass gets heated, and most part of it is lost to the atmosphere, the heat, and some part may contribute, but that will be very negligible, right? So this is when any radiation strikes a horizontal surface, what might happen to that radiation or that energy. Now we are generally interested in absorbing, when you are talking about the absorber of a solar collector. In any solar collector there will always be absorption, right? Only if there is absorption, the next thing would be the conversion. So that absorption, now let us focus on a solar thermal collector. So it converts solar energy into heat energy. So what gets absorbed becomes heat or thermal energy, and it will increase the temperature of some surface. So generally the absorption is done on, let's say, a plate which is called absorber plate, and absorber plate absorbs the radiation and it gets heated. Now once it gets heated, when you say it gets heated, the temperature is above atmospheric temperature. Now you have created some potential for heat transfer, or it is, because it is undesirable, we call it heat loss, right? So there is a surface, let's say you put just a simple black color plate in open, in sun, right? What will happen is, yes, the surface temperature of that will increase because it is absorbing solar radiation, but then the moment its temperature goes above atmospheric temperature, it will start giving out heat. Like it will start losing it to air which is moving over it. It will start losing it to the surroundings by even mode of radiation. So you are talking about different losses of heat, which is basically a heat transfer. Now you have, like in this B course, you have not yet formally studied the subject of heat transfer. We are not even going into details of that, and even this discussion, which is not that detailed that you will need a thorough knowledge of heat transfer. But yes, at diploma level you do study it, and like the very basics are already known to you. So the heat transfer by mode of conduction, the Fourier's law is well known to you. The heat transfer rate would be given by, like if it is passing through some, you can call it a wall of made up of some material having thermal conductivity K. The area perpendicular to the heat flow is A. The temperature difference between the two surfaces of that wall is delta T, and the thickness of the wall is L. Then Q dot is given by minus Ka delta T upon L. Right, so this is basically how the heat transfer, how to calculate the heat transfer. Of course, this is a one-dimensional case that you are talking about, and a steady-state case that you are talking about. So Q dot can be calculated as minus Ka delta T upon L. Right. So, main thing to understand is the basic principle. What is responsible for heat transfer by mode of conduction? What are the parameters that play a role? Like more the area, more will be the heat transfer rate. Similarly, higher the conductivity, it will allow more heat transfer to take place. Similarly, higher the temperature difference between the two sides, more will be the heat transfer rate. And similarly, it is inversely proportional to L. So if you increase the thickness, then the heat transfer rate would be lower. Right. So this is about the heat transfer by mode of conduction. Then the heat transfer by mode of convection. The basic governing equation for that is Newton's law of cooling. That is, it is equal to heat transfer coefficient, that is convective heat transfer coefficient, multiplied by the area and the temperature difference. The temperature difference is the potential for heat transfer. Right now, this is a very simplified way of the convective heat transfer rate, but getting H may not be that simple, as you will study it in more detail in the subject of heat transfer. That generally the most important job is to get the heat transfer coefficient, right? And there are so many considerations that go into it. Okay, so if you have H, and like you should know like what are the things which are affecting H, like the it is most of the times function of Reynolds number and Prandtl number. So Prandtl number depends upon the fluid properties, Reynolds number depend upon fluid property as well as the type of flow. So you might have some idea about the laminar flow and turbulent flow, and normally higher the velocity, better the heat transfer coefficient that you get, right? But again, we are not going into too much details of that. Now heat transfer by mode of radiation. You know this basic equation, the emissive power of a black body E is sigma into T raised to 4, where sigma is this Stefan Boltzmann constant 5.67 into 10 raised to minus 8 watt per meter square into Kelvin raised to minus 4. Now that is for black body. If it is a gray body, then your emissivity is a constant, and you can write it as as epsilon into sigma into T raised to 4. But if you are talking about heat exchange between two black bodies with exposed to each other only, then it will be emissive power or net rate of heat flow from surface 1 to surface 2, right? That would be given by this epsilon 1 into sigma into T1 raised to minus T1 raised to 4 minus T2 raised to 4, and the net radiative heat transfer between these two surfaces or any two surfaces is given by this general equation. Q dot is equal to area into the shape factor is also going to play a role, and J1 minus J2, which is radiosity. Okay, this is the heat transfer rate between surface 1 and surface 2. F12 is the view factor, and J is radiosity. Now radiosity is sum of two different parts, one the emission and the other the reflection, and this G is again nothing but uh, the um, emissivity into this constant Stefan Boltzmann constant and the temperature of the second surface T raised to 4, right? So these things have been depicted with the help of diagrams here. So these are the very basics of the different modes of heat transfer. It is just a kind of very basic introduction and recap of what you might be already knowing from the very basics that you have studied at perhaps two levels, one at the higher secondary level and or secondary level, and at your diploma level.